friends, it's Friday and it is our last day in chapter 5. So this is the last day you're going to work with the fundamental theorem. Last notes for this chapter, this module, and then we'll be looking at a test next week. So I want to wrap up our understanding of the fundamental theorem of calculus. Actually, let's back up here. All right, fundamental theorem of calculus says if you take a function and you integrate it starting at a and ending at b, then that is related to its antiderivative. And you first plug in b, and then you subtract when you plug in a. By the way, on the quiz, there were a couple of you that did that backwards, and you plugged in a first, the bottom one, and then the b on the top, which means all your answers were backwards. So that would be something to watch out for, making sure that you're doing the upper bound first. Okay, that is the fundamental theorem of calculus. But that fundamental theorem is very fluid. The relationship between little f and big F can be applied at lots of different levels. Like, for example, it can look like this. You can have f prime being part of the fundamental theorem of calculus, and f prime is going to go to regular f with b and a plugged in and subtracted. You could go from f double prime, and if you did, then you'd go back to f single prime with b and a plugged in. You could, you could do this for any relationship as long as they are in, one level of derivative apart from each other. Okay, and as long as the function is continues to be continuous, continues to be differentiable, then you can do these things. Okay, so just be fluid and understand that the fundamental theorem can be applied in multiple levels, just like the mean value theorem could also be applied in multiple levels. Okay, don't get just so stuck in one thing. All right, the other thing that the fundamental theorem can do, don't erase the notes you just wrote if you wrote those, but maybe move them to the side or something, is that you can use the fundamental theorem to find unknown parts. So suppose that between the f of b and the f of a, let's say that this part is unknown, but that this value is given. In other words, it is a known quantity. When you want to find something in math that's unknown, you want to get it alone. You want to move things around. So ideally, we would take this given and sling it over to the other side so that we have our unknown part of the equation alone. And so what that ends up looking like is that you'll have f of a in front of the integral from a to b of f prime t dt, and that will isolate f of b. So now your unknown part is all alone, and you can combine the other two sides of using your skills that you already know. So this would be given, and then the integral you could do with geometry, or you could do it with Math 9, or you could do it with an antiderivative, all depending on which section of the test it's on and what tools you have accessible to you. So it's so powerful because you can find the unknown then. You can find and express the unknown by getting it alone and having the other side be two things that you do know. Let me show you how that works. It's kind of like thinking of it as a initial condition accumulator function. You're going to start with a C amount. You'll have already been given that. It's giving somebody a head start and then accumulating points from there. It would be like if I gave everybody in the class 50% just by putting your name on something. Like I'm giving everybody this amount, and then you can accumulate after that. Okay, you don't start from 0, you start from a given amount and then move forward from that point. Okay, so let's say that you're asked to find f of x given a derivative that's impossible. Okay, that derivative, not whose antiderivative is impossible is what I meant to say. Okay, e to the negative x squared. That is not something that you can do geometry with. It's not something that you can do an antiderivative with. It is a complex irrational function. So how can you find f of x if all you have is that, but you also have this bonus little given value here? All right, everybody is given the head start of 3, starting with an x value of 7. All right, so you can now find f of x or express f of x starting with the bonus given value of 3. And from there, you can do an antiderivative of the irrational function if you start at the number 7, which is what the given value is connected to, and then end at an unknown, like I'm not sure yet where I'm going to end. In terms of area, we are starting with a value of 3, and then we are collecting or accumulating area from 7 on forward to some ending point, which we don't know what the ending point is yet, but that's how we're getting started. So this is called initial condition plus the area going to the right, starting from the number 7 and then moving to the right. So we've got this graph of a function that we can't do the antiderivative of by hand, but we're going to accumulate area, but starting specifically at the number 7. Okay, starting nowhere else. We're just setting it up right now, okay? It's all right. Okay, how about the g of function? Find g of x if its derivative is an irrational square root function of the sine of x, but you're given the head start initial condition of at g of 1, you're given 7 to start. So your expression for g of x is going to be, I know that it's going to start with a value of 7, and I can accumulate or evaluate area starting at the position -1 on the x-axis, ending, I don't know yet, so we'll call it b since it's on the upper bound. That'll make more sense. Ending somewhere of the square root of the sine of x dx. So we'll be moving along the x-axis, accumulating and picking up area, and stopping whenever I give you an interval to stop at. All you're doing is setting it up, okay? You're not asked to find anything yet. You're just asked to find g of x, which we did. We found g of x by expressing it in terms of 7 and another integral. Now this question is going to take it one step further. Find the function f of x, whose derivative is the tangent of x, and satisfying the given condition of f of 3 being 57. So let's start with that first. Let's find the f of x. F of x is going to start with a value of 57. This is good. This is like me telling you where its y-intercept is going to be, right? This is helping you determine antiderivatives can be parallel, lots of different antiderivatives, but this specific one we want has to go through the number 57. So we'll start with 57, and then from 3 to some ending value, we are going to accumulate area under tangent of x. All right, so we are setting this function up. Then, now I'm asking you to actually stop at the number 7. So f of 7 means still starting with 57, starting with the number 3 and ending at 7. That's our ending spot. So we're going to go from 3 to 4 to 5 to 6 to 7 and stop. And we're going to accumulate all the area under that and add it up together. All right, so I'd like you to get out your graphing calculators, and Mr. Lever's going to pause this video, and you're going to just make sure you're in the right mode and come up with the value of what f of 7 would be, starting at 57 and then accumulating. So with your calculator, you can use Math 9. So I'd like you to do that and compare your answer with your neighbor. All right, I'm back. You're back. I don't know how many of you got an error on that. So I realized too at the same time that I got a tolerance not met on my calculator when I did that, and I realized that I gave you an interval that's not continuous. So I gave you a bad interval. We can't go from 3 to 7 because tangent has an asymptote in that region. So shame on me for not double checking this ahead of time. So we are going to need to make sure we change our value so that we can actually stay within, I'm not going to like redo and re-record this whole thing. So we're just going to pivot, and we need to just stick with f of 4 because then we won't be crossing anything that we're not allowed to. So let's go to f of 4 instead. And then we do come up with an accumulated area. So 57.415 is the value of the function for f of 4. All right, moving on. We can also do it with a graph. So now no calculators, and we'll be using just the graph to answer the question. One thing that really pushes this to the next level, okay, this really is making your critical thinking skills kick in at a high gear, because the graph that we are given is the graph of f. But you'll notice all the questions are about the value of g. Okay, not the graph of f, they're the value of g instead, but there is a relationship between g and f. They will always give you that given relationship in the direction. So this figure is 2 line segments, and the relationship between g and f is that g is the antiderivative of f. So we are given that information. This is where I really recommend you do some pre-writing. And so I want you to be thinking about, you're going to need to know g, but you're also going to need something for g prime, and you're also going to need something for g double prime. So if we know that g is related to f by an antiderivative, we should also be able to find g prime. G prime should be the derivative of what we were given. So based on your homework from Wednesday and Thursday, that turns out to be f, we're back to f, with the upper bound of x plugged in and remembering the chain rule, minus f with the lower bound plugged in and remembering the chain rule, which ultimately we can simplify to be just f of x. And then g double prime would be the derivative of that. So it's going to be the derivative of f of x, which is simply f single prime. So g double prime is related to f single prime. G single prime is related to regular f. And regular g is the antiderivative of f. All these relationships, that's what makes the critical thinking just really next level. Okay, so these 3 things is all part of your pre-write. Now that's going to help us actually answer the 3 questions they want us to do. First question, find g of -1. Well, we want the relationship of what g is to f. So looking at what we are given here, x is the upper bound. So -1 should be our upper bound of f of t dt. In other words, we want to find the area of the graph we're given between the bounds of 0 and -1. Okay? Of the graph we're given between the bounds of 0 and -1. So we will be going backwards between those values, which is going to be a triangle that's backwards. So we simply use the geometry to say that's going to be negative 1/2 of the triangle 1 times 3. In other words, negative 3/2. We also are asked to find g prime of negative 1. Now, based on our pre-write, g prime of negative 1 is connected to f of negative 1. F of negative 1 is not the area, it's simply the value of the graph. All right, so the value of the graph is not the area, it's not the slope, it's just simply the point that's sitting at negative 1. And the point that's sitting at negative 1 is 0. And then lastly, we're asked to find g double prime of negative 1, which is related to f single prime of negative 1, which is the slope through the point at negative 1. So looking at the slope along that linear piece, you count the rise over run, so that's up 3 over 1. In other words, that value is 3. So we could find all 3 values for g by relating it to its relationship to f. Super common tactic for AP questions to be able to make that connection from a function of one letter to a function of a different letter by knowing what the relationship is. Let's keep thinking about this same graph. For what values is g increasing, and explain your reasoning? The reasoning is going to be what's going to get you, a lot of the points here. So you want to start with, I would start with actually your justification. The function g will increase, and the definition of that is anytime g prime is positive. That's not a new concept. We learned that in first semester. G will increase anytime g prime is positive. Here's the connection. We want to connect it to f, aka anytime. All right, what was g prime again? Okay, thinking about our pre-write here, g prime is regular f. So aka anytime f is positive. So let's look at the graph. When is f positive? Not the area of f, not the slope of f, just f itself. When is f positive? So Mr. Lever's going to pause it here, and I want you to talk with your neighbor about when you think f is positive. All right, when did you think f was positive? Well, hopefully you identified the sections of f that are above the x-axis, which is the interval from -1 to +1. And that answers the question. Okay, when is the value of g increase? G will increase anytime g prime is positive, aka anytime f is positive, and that happens between -1 and 1. We could ask a converse question. What are the values when g would decrease? He would answer it in a similar way. The function g will decrease anytime g prime is negative, aka anytime f is negative. And then you need to focus in on the intervals of f, which are below the x-axis. Again, not the area of f, not the slope of f, simply the values of f, which are below the x-axis. All right, this is the last question about this graph. For what values is g concave up? So model your answers. You can kind of get into a rhythm. The function g will be concave up anytime g double prime is positive. AKA, so what was g double prime? Well, if g single prime was f of x, then g double prime was f prime of x. So aka anytime f prime is positive. All right, well, how do we figure out what f prime is positive? Well, we've got the graph of f. So I want you to, again, we'll pause it here, talk with your neighbor. When do you think f prime is positive? All right, hopefully you and your neighbor agreed that f prime would be positive anytime the slope of the graph of f is positive, which is the whole interval from -2 to 0. All right, so hopefully you guys got that. Okay, the next graph it is similar. We've got several triangles and everything going on here. Actually, just for the sake of time, want you to skip slides 41, 42, and 43 and go to slide 45, actually 44 as well. I want to look at a graph that has a curve to it. If you want additional practice, you can watch last year's video, a previous video that has those other dealing with that other graph, this one, dealing with that. You can go back and watch that, but I would like to make sure we talk about this one. So here's another example of a time where we are given a graph of f. Okay, so this is the graph of f, but all of our questions have to do with s. So the graph is f, but the question is s. So again, such a common strategy, common technique for them to assess if you really are reading well and understanding what they're asking. So s and f are related. S is the antiderivative of f, which again is represented as the area of f. So that answers the first question. What is the meaning of the defined function of s of t? So s of t means the area under the f of x graph beginning at 0. You won't always begin at 0, but this one does because that's what the lower bound is. That's given to you as your initial condition. So S of t is the area under the graph beginning at 0. Let's talk about velocity and acceleration. So velocity is defined as s prime of t. S prime of t needs to be the derivative, which would be f of t, the graph itself. And then acceleration will be s double prime of t, which will be f single prime. So s double prime is connected to f single prime. The slope of the f of x graph, and whereas the one above it is the value, the plane value of the f of x graph. So to summarize, that f graph has 3 ways it can tell us things. If we find area, it tells us one thing. If we just evaluate its position, its value, that tells us one thing. And if we evaluate its slope, it tells us something else. So all of those things are important. Okay, next question. What is the initial position of the particle? The word or the phrase initial position always implies that time is equal to 0. And so we want to find the s value when time is 0. So where does time go? Well, according to the given, the time is the upper bound. So we want to have our lower bound be 0 and our upper bound be 0 of f of x dx. And one of the basic properties is if you start and go nowhere, then you've achieved zero area. But that meaning is that we are starting on the origin. It's sitting on the origin. How do I know it starts at the origin? Because the directions say the position of the particle is moving along the coordinate axis. So it's moving side to side along the coordinate axis. So if it has a value of 0, position of 0, it's sitting at the origin. So what's the position of the particle at 3? So we want to do S of 3, which means starting at 0, we want to end at 3, which means I am evaluating the area under the graph from 0 to 3. And as I look at that area, I realize that it is a triangle underneath the x-axis. So it should have a negative value. So 1/2, and then 3 times 6 for my triangle, which is -9. So that means it's moved 9 to the left. Okay, so we've started at the origin and now we've moved 9 left. To follow up, to finish it, when will the particle get back to the origin? When will it return? Well, if it's moved 9 left, it's got to move 9 right to get back to the origin again. And so if I follow the area, I will be moving 9 right in that next triangle, which is an equivalent. Okay, we have symmetry going on here. So the particle will return to the origin at S of 6. Because S of 6 will be the 0 to 3 combined with 3 to 6, which will be -9 plus +9, which is back to the origin again. So I've returned. So the graph can tell us the story of how this particle is moving. As it pushes past the number 6, it continues to accumulate additional positive area, which means it continues to move beyond the origin and move towards to the right. Here's a few questions. I wanted to highlight these because a couple of you, this was the extra credit question, and some of you nailed it, totally nailed it, but let's go over it so that more of you can get it right next time. When we talk about moving toward the origin, there's 2 things you have to check. Moving toward the origin means the position and the velocity must have opposite signs. If you want to move away from the origin, the position and the velocity must have the same sign. So you can't answer this question without comparing those 2 things. So I find it helpful to set up intervals so that I can compare the position and the velocity at the same time with plus or minus symbols. So I'm going to go from 0 to 3, then 3 to 6, and then I think I'm going to go from 6 to 7 because I do have a data point there. And then I'm going to go from 7 to, it's a little bit more than 9. I don't know exactly what it is, but it's 9 plus. And I want to compare the position, which is the S of t, and I want to compare it to the velocity, which is the S prime of t. And if you remember from our given, S of t is the area. So from 0 to 3, we clearly have negative area. We've accumulated only negative area. From 3 to 6, it gets a little tricky. You've accumulated negative area so far. And as you push past 3 and start to accumulate, you might think, okay, well, what if I get to the number 4? I'm starting to accumulate positive area, but it's not enough positive area to counterbalance the negative area that I'd had before. So even at the number 4, I'm still a total of negative. Okay, we have to think of it. This is all total. What about if I go to the number 5? If I tested the number 5, go to number 5, I've still accumulated more positive area, but it's not enough, so I'm still negative. And if I push all the way up just to below the number 6, I still have only accumulated a total of negative area. When I finally get to 6, I'll be back to 0 again. Remember, that's when you return to the origin. And when you push beyond 6, you finally have enough positive area where your position would be considered positive. And then for sure, from 7 to 9, you are accumulating all that positive area. So be thinking of an accumulation, not for the position, not just above or below the x-axis, but a total accumulation. When we move to velocity, now we're at s prime. And remember that s prime is simply f of t. That is simply above or below the x-axis. It is not an accumulation at all. So from 0 to 3, the graph is for sure below the x-axis. And from 3 to 6, it is above. It is not an accumulation anymore. We're not adding area. We're just looking at the value of the function. And all of these are positive. So if I am looking for opposite signs, the only place I have opposite signs is between 3 and 6. So that is the only time that the particle would be moving toward the origin. All of the rest of the times it will be moving away from the origin. The first 3 seconds, it's moving away from the origin in a negative sense. And then from 6 to 7, and then to 8 and to 9, it's moving away from the origin in a positive sense. So by the time it gets to time 9, on what side of the origin does the particle lie? It's on the positive side of the origin. Or we could say the right side. All right, last question. What is the velocity of the particle at time 3, the acceleration, and what does that mean? So our velocity is s prime. S prime is f of t. So s prime of 3 would be just f of 3. That's not the area at 3. It's simply the position of the function at 3, which is sitting right on the x-axis, so that has a value of 0. If the velocity of the particle turns out to be 0, that means it is sitting at rest. What's the acceleration? So the acceleration would be s double prime of t, which would be f single, which is connected to f single prime of t. So s double prime at 3 is connected to f single prime at 3, which is the slope through that point if we count our rise over run. And so looking at the graph, counting the slope right here, we count up 6 units, but only over 3. It's not to scale, so you have to make sure your eyes don't trick you. It is up 6, but over 3. And so the acceleration is 2, which means it is accelerating. It has positive acceleration. So what does it mean about the particle's movement? It means it's at rest, but it's accelerating. It's almost like sitting at a stoplight and you're in neutral, so you're not moving, but you're really revving the engine, right? You are at rest, but you are ready for some positive acceleration. So it's at rest, but it's sure getting ready to speed up. Not speeding up yet, but it's sure getting ready for that. All right, that is a wrap on chapter 5. All right, so save up all your questions for Monday, or mark them in Canvas, and I will do my best to respond to you. But Monday and Tuesday we'll hammer out, we'll go over your quizzes, and then we'll hammer out any other questions you've got. All right, thanks, Mr. Lever. I appreciate you.